Good morning, all of you. Welcome to Sri Jayendra Rank Zone. Today we are going to discuss 16 group element continuation. In the previous class, we have done about the general trends and periodic properties of 16 group elements, that is sulfur and oxygen. Now we are going to discuss more about 16 group elements. So please listen carefully. Yes, 16 group elements. Now, since we have completed already general physical properties and chemical properties along with some other additional properties, now in this session we are going to do preparation and properties of oxygen and sulfur compounds. Let us see now. So dioxygen preparation. Oxygen is, it is O2, it exists as diatomic molecules, that's why it is called dioxygen preparation. So now we are going to do dioxygen preparation. First, by thermal decomposition of salts. Dioxygen is prepared by the thermal decomposition of salts. So what are the thermal decomposition of salts we are discussing now? Yes. Yes. First, by thermal decomposition of salts. Sodium nitrate. Sodium nitrate on heating strongly forms sodium nitrate along with oxygen. Sodium nitrate along with oxygen. Potassium chloride on heating strongly in the presence of manganese dioxide forms potassium chloride and oxygen gas. So these are the two preparations of dioxygen, that is by the thermal decomposition of salts. Here sodium nitrate and potassium chloride are the salts. By the thermal decomposition of oxides of metal. So metallic oxides such as lead dioxide, silver oxide on heating strongly will form lead oxide along with oxygen and silver along with oxygen. So these are the preparations of oxygen. Yes, we have to remember the equations only, not the need to remember also. Just you can understand it. Now, by the decomposition of hydrogen peroxide, already we know hydrogen peroxide on heating strongly in the presence of manganese dioxide as a catalyst, it forms water and oxygen gas. Next, by the electrolysis of water. So, this also we can do by using electrolysis of water. So, when you do when you pass current to water, it forms hydrogen gas and oxygen gas. Hydrogen gas is formed at cathode, oxygen gas will be formed at anode. So this is called electrolysis of water. So these are the main preparations of oxygen, dioxygen. Now, physical properties of dioxygen. It is a colorless and odorless gas. It is soluble in water to support marine and aquatic life, and it has paramagnetic in nature. Already you know oxygen molecule is paramagnetic in nature. Next, chemical properties of dioxygen. Oxygen directly combines, since oxygen is highly reactive, it directly combines with all metals and non-metals to form their respective oxides. It will not combine with noble metals like gold, silver, or platinum, only with few metals, that is gold, silver, and platinum. It will not combine directly, whereas with other metals and non-metals, it directly combines. For example, calcium on combination with oxygen forms calcium oxide. Phosphorus, when burns in air, it forms phosphorus pentoxide, and zinc sulfide on oxidation gives zinc oxide plus sulfur dioxide gas. Aluminium on oxidation gives Al2O3. Carbon on oxidation gives carbon dioxide. And CH4, that is methane. Any organic compound when burns in air oxygen, it forms carbon dioxide and water. So these are the chemical properties of oxygen. So it's very easy. And oxygen is highly reactive due to, as it is highly reactive, it will combine with almost all the metals and non-metals and form their respective oxides. Metals, with metals it form metallic oxides, with non-metals it form non-metallic oxides. And already you know metallic oxides are basic in nature, non-metallic oxides are acidic in nature. And we have seen in the previous session nature of oxides, that is acidic oxides, basic oxides, neutral oxides, and amphoteric oxides. So next, uses of oxygen. Oxygen is used in oxyacetylene building. Oxygen is used in oxyacetylene torch. It is also called as oxyacetylene torch. Its temperature is around 3000 degrees C. With this high temperature, around approximately this is 3000 degrees C. With this high temperature, it can be used for welding purpose, that is joining of metals, joining of metallic plates. That is called welding. It is used in the manufacture of metals and steel also. Oxygen cylinders are used in hospitals, flying, and mountaineering because they need oxygen. So the patients who are suffering from breathlessness or breathing problems, they use oxygen cylinders. So oxygen cylinders are used in hospitals, flying and mountaineering. It is used for combustion of fuels. Oxygen is used for combustion of fuels. Oxygen is an essential component for normal respiration. As you already know, without oxygen, we cannot survive easily. It's very difficult to survive without oxygen because oxygen is necessary for breathing. Next, ozone. The compound of oxygen is ozone. So ozone is an allotropic form of oxygen. Ozone layer protects the Earth's surface from ultraviolet radiations of sun. And when the ozone layer gets depletion, it results in the formation of global warming. Global warming. Why? Because due to depletion of ozone layer by the means of pollutants, due to depletion of ozone layer, depletion means keeping whole. So due to depletion of ozone layer, global warming takes place. So to prevent this, we have to save global warming takes place. So to prevent this, we should protect the ozone layer. And ozone layer protects the Earth's surface from ultraviolet radiations coming directly from the sun to the Earth. So because of ozone layer only, all the ultraviolet radiations are not coming directly from the sun. That's why it's very, very important. Next, preparation of ozone. When a slow, dry stream of oxygen is passed to a silent electric discharge, for oxygen, if you pass current, silent electric discharge, ozonized oxygen is formed. So it is nothing but ozone is formed, and the reaction is delta H is positive endothermic reaction, and delta S is a change in entropy is negative because the order changes to disordered is negative, and delta G is positive. That is delta G, that is change in Gibbs energy is also, Gibbs free energy is also positive. So these things are important. So when a slow dry stream of oxygen is passed to a silent electric discharge, ozonized oxygen is formed. What is formed? Ozonized oxygen. So it is a reversible reaction. Next, physical properties of ozone. It is a pale blue gas, dark blue liquid, and violet black solid. It is thermodynamically unstable. This ozonized gas is thermodynamically unstable. It is a pale blue gas, dark blue liquid, and violet black solid. If the concentration of ozone rises above 100 parts per million, the concentration of ozone rises above 100 parts per million in the atmosphere, it is difficult to breathe. High concentration of ozone can be dangerously explosive. So these are the physical properties of ozone. So if the concentration of ozone rises above 100 parts per million, it is difficult to breathe. And that's why these pollution areas, especially in the winter season, will find this. Next, chemical properties of ozone. Ozone is a good oxidizing agent due to the liberation of nascent oxygen. As nascent oxygen is also known as just born oxygen, as it is highly reactive. So ozone acts as a good oxidizing agent. So it oxidizes lead sulfide to lead sulfate, potassium iodide to potassium hydroxide and iodine, and mercury on reaction with ozone forms mercuric oxide plus oxygen. This is also called as tailing of mercury. This already we have seen in the preparation and the properties of oxygen. So these are the oxidizing reactions of ozone. Not only this, so many others are also there. So a few important reactions we have given. So ozone is a good oxidizing agent. Why? Because due to the presence of nascent oxygen. And if you take ozone with any other, so ozone is highly unstable, so it dissociates to form oxygen plus nascent oxygen. This nascent oxygen is highly reactive and it attacks the lead sulfide to lead sulfate, potassium iodide to iodine, mercury to mercuric oxide, and so on. Next, structure of ozone. Ozone is angular molecule. Its bond angle is 117 degrees. Both bond lengths are equal and equal to 128 picometers due to resonance. So this is called ozone. So ozone is nothing but its angular molecule, just like water. Bond angle is 117 degrees, and both bond lengths are equal and equal to 128 picometers due to resonance. Next, uses of ozone. It is used as germicide. Germicide are nothing but to kill insecticides in field, disinfectant, and for sterilization of water. So the sterilization of water will be done in clinics so that they'll keep all the disposable syringes. So that is sterilization of water. So ozone is used as germicide, disinfectant, and for sterilization of water. It is used for bleaching oils, ivory, flour, starch, etc. It acts as an oxidizing agent in the manufacture of potassium permanganate. So ozone acts as an oxidizing agent in the manufacture of potassium permanganate. I hope it is clear. So these are the important uses of ozone. Next, quantitative estimation of ozone. Ozone is estimated quantitatively by iodometric titrations. This we have done in stoichiometry. Ozone is reacted with excess of potassium iodide in the presence of buffer solution. pH is equal to 9.2. What is a buffer solution? It is nothing but a solution which contains of salt of, so if it is acidic buffer solution, weak acid and it's salt with salt solution, and it's salt with weak acid and is acid with salt solution. It is called buffer solution, acidic buffer solution. Weak base and it's a salt with salt solution. It is called, and it's acid with base with salt solution. It is called basic buffer solution. So this buffer solution, ozone is reacted with excess of potassium iodide in the presence of a buffer solution. So pH is called 9.2. Iodine is liberated. Liberated iodine is estimated by titrating against the standard sodium thiosulfate solution. What is standard thiosulfate solution? Na2H2O3 is called sodium thiosulfate. So the liberated iodine combines with sodium thiosulfate using starch indicator near the end point. By this we can do titration. Titration means estimation of concentration. That is to find the concentration of a given solution. To find the concentration of a unknown solution. So what is titration means? To find concentration of unknown solution. Finding the concentration of an unknown solution. To find the concentration of unknown solution, we will do titration. Unknown solution. This is called titration. So this is called iodometric titrations, because iodine is used. So the iodine is found from ozone on reaction with potassium iodide. Potassium iodide combines with ozone and forms iodine is liberated. So I2 is liberated. This reaction already we have seen in previous slide. I hope it is clear. Next, sulfur dioxide. Now important compounds of sulfur. First we have sulfur dioxide. Sulfur dioxide is formed when sulfur is burnt in air and it is acidic in nature. Sulfur dioxide is acidic in nature. Sulfur dioxide is obtained by a product of in roasting of sulfide ores. We have seen in metallurgy that sulfide ores are being roasted. So how these sulfide ores are roasted? Because to convert the given sulfide ore into its oxide, we have to do roasting process. Roasting is a process in which the ore is heated strongly in the presence of air. Roasting is a process in which the ore is heated strongly. Roasting is a process in which heating of ore strongly in the presence of air. Heating of ore strongly in the presence of air is called roasting. In the presence of air. To convert the ore into its oxide, sulfide ore into oxide. To convert sulfide ores to its oxide, we have to do roasting process. So this is the formation of sulfur dioxide takes place as byproduct. In the laboratory, it is readily generated by treating sulfite salts with dilute sulfuric acid. Sulfite salt, sodium sulfite, and with sulfuric acid, it forms water and sulfur dioxide gas. So these are the preparations of sulfur dioxide. So in this, the byproduct is sulfur dioxide. In this, the main product is sulfur dioxide, and here also sulfur dioxide is formed. So sulfur dioxide is acidic oxide. Next, properties of sulfur dioxide. Sulfur dioxide is a colorless gas with pungent smell. It dissolves in water to form sulfurous acid. When sulfur dioxide is dissolved in water, it is formed sulfurous acid. That's why the anhydride of sulfurous acid is sulfur dioxide. We can write the anhydride. The anhydride of sulfurous acid is sulfurous acid means with if you remove water from sulfurous acid, that is H2SO3. The anhydride of sulfurous acid is sulfur dioxide. It reacts with sodium hydroxide to form sodium sulfide, and it combines sulfonyl chloride. It is used for the manufacture of mustard gas. So it reacts with chlorine to form an additional compound called sulfuryl chloride. This sulfuryl chloride combines with alcohols and forms alkyl halides. I hope it is clear. Next question. Sorry, next topic. Properties of sulfur dioxide continuation. Moist sulfur dioxide behaves as a bleaching agent and reducing agent. So for example, if you take moist sulfur dioxide, so ferric ions on reaction sulfur dioxide forms ferrous ion and it forms nested hydrogen or H plus ions. Similarly, if sulfur dioxide on reaction manganese sulfate, sorry, potassium permanganate, it forms potassium sulfate or manganese sulfate. Manganese ion along with potassium sulfate. So this is the properties of sulfur dioxide. Next, sulfur dioxide has a bent structure. This structure is important due to sp2 hybridization of sulfur. As it has lone pair of electrons, so it will have bent structure. It will not have similar structure like sp2. Generally, sp2 means planar triangle. So, but here it is taking bent structure due to lone pair of electrons on sulfur atom. Due to lone pair of electrons on sulfur. That's why it is forming bent structure. The bonding is 119 degrees. It is a resonance hybrid of two contributing structures, one side double bond and the other side single bond. So here plus charge and here minus charge. The SO bonds are of same length. Either double bond or single bond, they are of same length. So I hope it is clear. So this is the structure of sulfur dioxide. What is the hybridization of sulfur dioxide? It is sp2 hybridization. What is the shape of sulfur dioxide? It has bent structure. Next, use of sulfur dioxide. Sulfur dioxide is used as an anti-chlor, disinfectant and preservative. Anti-chlor, disinfectant and preservative. What is this anti-chlor means? Anti-chlor means here for removing chlorine. For removing chlorine, we'll use this sulfur dioxide, chlorine gas. So that's why it is called anti-chlor and disinfectant and preservative. Sulfur dioxide is used in refining of petroleum and sugar. Sulfur dioxide is used in refining of petroleum and sugar. That's why we'll say nowadays sulfur-free sugar. Actually, we have to use sulfur-free sugar. Otherwise, it is harmful. So if you take sulfur-free sugar, even though it is a bit costly than normal sugar, because it is not harmful. We have to consume only, always we have to use sugar as sulfur-free sugar. Otherwise, we'll have side effects. Now, sulfur hexafluoride is known, but sulfur hydrogen fluoride, that is, sorry, sulfur hexahydrogen is not known. Why? Because fluorine is strongest oxidizing agent, so that's why it can form with sulfur, but hydrogen is not an oxidizing agent, it's a reducing agent. Hydrogen is a reducing agent, that's why it is not known. I hope it is clear. Next, example 2. Give the test to identify sulfur dioxide gas, hydrogen sulfide gas, and ozone gas. Very, very easy. So what are the tests for sulfur dioxide and ozone gas and hydrogen sulfide gas? Let us discuss now. So for sulfur dioxide gas, the test is nothing but what? So when sulfur is burnt in air, it forms sulfur dioxide gas. Sulfur is burnt in air, it forms sulfur dioxide gas. So it is a colorless gas and it is acidic in nature. Acidic in nature. Next, hydrogen sulfide and with pungent odor. It is what? Pungent odor. So any test you can convert. Hydrogen sulfide, how to test hydrogen sulfide gas? It is a pale yellow liquid, pale yellow gas. So pale yellow gas with pungent odor, with the pungent odor. And ozone, how to give the test to identify ozone, how to identify ozone? So it is, oxygen is a colorless liquid, but ozone is pale blue liquid, which does not support combustion, does not support combustion. So these are the tests for sulfur. Not only this, so many tests are there. You can take any test from the slides. Sulfur dioxide, hydrogen sulfide, and ozone. I hope it is clear. Next. So Next topic in this chapter, we are done up to sulfur dioxide. Now we'll do more about sulfur, that is oxyacids of sulfur in this class. Yes. Next topic, oxoacids of sulfur. Like how we have done oxoacids of nitrogen, phosphorus. Now we are going to do oxoacids of sulfur. This is very, very important for competitive exam. So please note down all the points in this topic. So they can ask any question from this chapter. So that's why oxoacids of sulfur is very, very important. Let us see now. Sulfur has a number of oxoacids in which sulfur is sp3 hybridized. First point. In all the oxoacids of sulfur, sulfur is always sp3 hybridization. And basicity of all oxoacids is 2. Basicity of all oxoacids is 2 means it has 2 replaceable hydrogen atoms. 2 replaceable hydrogen atoms, or it has 2 OH bonds. So number of OH bonds gives you basicity of the acid. So sulfur has number of oxides. Why it is forming so many number of oxides? Due to availability of d orbital. Due to the availability of empty d orbital. Due to the availability of empty d orbital. Due to the availability of empty d orbital, sulfur forms many oxides. Even it can also form many compounds. So usually sulfur exists in +2 state, +4, +6, and -2. So it will exist all these oxygen states. +2, +4, +6, and -2. I hope it is clear. Let us discuss now what are the important oxides of sulfur. See, first one, sulfurous acid. Sulfurous acid has one lone pair of electrons. So it has 2 OH groups. So basicity is equal to, as I told you, all oxides of sulfur has basicity 2 because they have 2 OH bonds. So this is called sulfurous acid, H2SO3. It is less acidic than sulfuric acid. And the oxygen state of sulfur in this is equal to how much? So H2SO3. H2SO3 means here oxygen state is equal to, implies 2 plus x minus 6 is equal to 0. Implies x is equal to +4. So the oxygen state of sulfur is equal to +4 here because 2 plus 1 plus 3, 4. And here the oxygen state of sulfur is 6 plus 6 because it is sulfuric acid, strongly acidic in nature. It is also called as king of chemicals. As I already told you, sulfuric acid is called as king of chemicals. It is used as dehydrating agent, etc. So it has 2 OH bonds and 2 double bond SO bonds, 2 SO bonds and 2 OH bonds, SOH bonds. And next, thiosulfurous acid, H2S2O2, it has one lone pair and it has 2 sulfurs. So 2 sulfurs and 2 OH bonds along with 2 electrons. So the oxygen state of these 2 sulfur is 2x. Sorry, I'll write it again here. How to find oxygen state of sulfur in this compound. So here I'm doing it now. Please note it down. So here hydrogen is 2 plus 2 plus sulfur is, we have to find 2x minus 4 is equal to 0. And plus 2x minus 2 is equal to 0. And plus x is equal to 2x is equal to 2. And plus x is equal to +1. So oxygen state of sulfur is +1 here, and here also +1. Lower oxygen state. That's why it is less acidic. Next, thiosulfuric acid. Thiosulfuric acid has 2 OH bonds, and this is the formula for thiosulfuric acid, that is H2S2O3. Next, dithionous acid. Dithionous acid, H2S2O4, is the structure. It has 2 lone pairs of electrons and 2 sulfur atoms. Dithionic acid, it is H2S2O6. H2S2O6 with 4 SO bonds, SO, and 1 SOH, 2 SOH bonds. I hope it is clear. All these points are very important. Structures especially, they are important. They'll ask number of OH bonds in sulfuric acid, number of OH bonds in sulfurous acid. So in all those OH bonds, it is equal to 0 because the basicity is 2. And number of SOS bonds also they'll ask. Number of SS bonds in dithionous acid, it is 1. Number of SS bond in dithionic acid, it is 1. Number of SO bonds in dithionic acid and SS bonds, S double bond S only one, S double bond O one. Like that, they'll ask any question they can ask from all these structures. So these structures are very, very important. So please note it down. Next, disulfurous acid H2S2O5. Disulfurous acid H2S2O5. So it is disulfurous acid, pyrosulfurous acid H2S2O5. S, S, and SO. One SS bond. It has how many SS bonds? One SS single bond. One SS bond. Two OH bonds is common for all. Very, very important. And since it has two OH bonds, basically it's two. And SO bonds is double bond O bonds. How many are there? One, two, three. Three SO bonds and one lone pair. One lone pair. So all these are the points. Next, similarly, disulfuric acid H2S2O7 is also called as oleum. This is observing preparation of sulfuric acid by contact process. So this is called oleum. So oleum has two and one SOS bond. How many SOS bonds? One SOS bond and one, two, three, four. Four SO SW bond O bonds and two OH bonds. Two OH bonds. Very, very important. Oleum. SOS bonds, only one SOS bonds. Similarly, next, peroxomonosulfuric acid is also called as Caros acid. Caros acid formula is H2SO5. Very important structure. They ask this question many times. So, how many peroxy bonds are there in Caros acid? One peroxy bond. One peroxy bond. This is called peroxy bond. So, one peroxy bond. Two S double bond bonds and two OH bonds. So these are the information based on Caros acid. Peroxodisulfuric acid. So what is also instead of sulfur in our Caros acid? Since it has only one peroxy bond, so that one oxygen is 2, 2. So here 2 plus 2, 4, 4 plus 1, 5, 5 plus 1, 6, 6 plus 1, 7. So total it is 7. So 7 means sulfur will be plus 6 state. Because also instead of sulfur, it is plus 6 state because here it is 2, and here 1, 3, 3 plus 2, 5, 5 plus 1, 6. So 6. Peroxodisulfuric acid Marshall's acid is equal to H2S2O8 and it has SOOS bond. One SOS bond and two OH bonds. Two OH bonds. Double bond with double bond. So four SO bonds. Four SO bonds. So all this information is very, very important. So it's very difficult to remember, but you have to practice it. Yes. It's clear. Next. Next, sulfuric acid. Very, very important. Sulfuric acid is the most important industrial chemical worldwide. It is also called as king of chemicals. It is manufactured by contact process. So manufacture of sulfuric acid by contact process. So it's easy to understand. It's very important also. So when sulfur is burnt in air, sulfur burners, it forms sulfur dioxide. First, sulfur is burnt in air to form sulfur dioxide, and this can be done in sulfur burners. When sulfur dioxide is purified by removing dust and arsenic impurity. Second step, what you have to do? This sulfur dioxide is purified by removing dust and arsenic as an impurity. Arsenic is a catalytic poison for vanadium pentoxide catalyst. So, to deactivate vanadium and to deactivate the vanadium pentoxide catalyst, this arsenic is helpful. That's why arsenic is a catalytic poison, negative catalyst. Catalytic poison is what? Inhibitor. What we'll call it as. In the previous chapter, we have seen what is inhibitor. The inhibitor. So the inhibitor will prevent the action of catalyst. So that's why if you remove arsenic, vanadium pentoxide can act properly. So for the proper functioning of vanadium pentoxide as catalyst in the reaction, we have to remove arsenic as an impurity. Next, this sulfur dioxide so formed. This sulfur dioxide so formed contains arsenic as an impurity, and it can be removed as an impurity because it acts as inhibitor for catalytic activity. Then the sulfur dioxide is converted to sulfur dioxide. Sulfur dioxide is converted into sulfur dioxide in the presence of vanadium pentoxide as catalyst. In the presence of vanadium pentoxide as catalyst. So for the activity of catalyst, we have to remove arsenic. So sulfur dioxide combines with oxygen and forms sulfur dioxide. Delta H is negative. Optimum temperature is 670 to 720 kelvins, and the optimum pressure is 2 atmospheres. I hope it is clear. So this is the preparation of sulfur dioxide. Next we have preparation of after sulfur dioxide. Sulfur dioxide is absorbed in concentrated sulfuric acid to get oleum. This sulfur dioxide so formed is absorbed by concentrated sulfuric acid to get oleum. So to prepare sulfuric acid, we need to take concentrated sulfuric acid again. So this oleum on water on reaction on hydrolysis forms sulfuric acid. So these are the four steps. First step, formation of sulfur dioxide. Second step, removing of inhibitors for the catalyst. Third step, formation of sulfur dioxide. Fourth step, sulfur dioxide is converted into oleum, and fifth step, oleum is converted into sulfuric acid, and oleum is mixed with calculated quantity of water to get 98% sulfuric acid. So whatever sulfuric acid you have got, it is 98% sulfuric acid. 98% sulfuric acid means 98% it is pure. I hope it is clear. Let us see the diagram now for this. As I told you, sulfur burners, air is been released to sulfur, so it forms sulfur dioxide. Impure sulfur dioxide dust will be removed in this chamber, and water is sprinkled on this so that the dust and arsenic is removed, and then this concentrated sulfuric acid is sprayed on the sulfur dioxide along with oxygen. Formation of sulfur dioxide takes place, and this arsenic purifier containing gelatinous hydrogen hydrated ferric oxide, what is this called? Arsenic purifier containing gelatinous hydrated ferric oxide, and this preheater, then catalytic converter. This sulfur dioxide is converted into sulfur trioxide here. Here sulfur trioxide is formed, and then this concentrated sulfuric acid. Why here concentrated sulfuric acid is sprayed here? To absorb water. To absorb water, because sulfuric acid is a good dehydrating agent. So to absorb water from this, we have to use this concentrated sulfuric acid initially. Then after formation of sulfur trioxide, then again it is sprinkled with concentrated sulfuric acid, which results in the formation of oleum, and this volume, when you dilute it with water, it forms sulfuric acid. So finally sulfuric acid is formed. So volume on reaction with water, it forms sulfuric acid. So this is called contact process. So first case, sulfur burners will be taken, and air is blown into sulfur burners. From the air it combines with sulfur along with some sulfur present in it. So this becomes sulfur dioxide and oxygen along with impurities. Then water is sprayed. So that is dusty impurities will be removed by the means of spraying of water, and to remove water they'll use concentrated sulfuric acid spray, so that the concentrated sulfuric acid is to absorb water, will absorb water here. Only dry sulfur dioxide along with some oxygen will go up into this, where arsenic purifier, where arsenic is being removed by using arsenic purifier, because already we have given that with sulfur dioxide some amount of arsenic also is present as an impurity. This, if arsenic is present as an impurity, this catalyst activity will be zero. So that's why we have to remove this arsenic. And after passing to heating, that is preheater, in the presence of catalytic chamber, now we have to introduce the sulfur dioxide gas and oxygen along with oxygen in the catalytic chamber, where we have vanadium pentoxide as catalyst. Then it gets converted into sulfur dioxide. This sulfur dioxide slowly is being absorbed, is being allowed to concentrated sulfuric acid is sprayed on the top, from the top. This is quartz glass, and from the top we'll be spraying what? Concentrated sulfuric acid, so that it forms volume, and finally this volume changes to sulfuric acid. So this is called preparation of sulfuric acid by contact process. So this process is very important. They'll ask in the examination based on these questions. Next, properties of sulfuric acid. Sulfuric acid is colorless, dense, oily liquid with a specific gravity of 1.84. Sulfur dioxide is colorless, dense, oily liquid with specific gravity of 1.84. It freezes at 283 kelvins and boils at 611 kelvins. It dissolves in water with the evolution of large quantity of heat. Sulfuric acid is dissolved in water with the evolution of large quantity of heat. Hence, concentrated sulfuric acid must be added slowly into water with constant stirring in order to prepare dilute sulfuric acid. So, to get dilute sulfuric acid, we have to use concentrated sulfuric acid must be added slowly in water with constant stirring. We have to keep on mixing in order to prepare dilute sulfuric acid. I hope it's clear. Next, in aqueous solution, it ionizes into two steps. Sulfuric acid ionizes in two steps because it contains two hydrogen atoms, that is, two irreplaceable hydrogen atoms. So first step, what happens? It forms H3O plus HSO4 minus. And second step, this HSO4 minus and this Ka1, that is, what is this Ka1 is called? This Ka1 is called what? Dissociation constant is greater than 10. And second, dissociation constant of acid. So in the first case, it produces only one H plus and it combines with water and forms H3O plus. Second case, this HSO4 minus combines with water and forms H3O plus again and forms SO4 2 minus. This is called Ka2, the dissociation constant of second acid, that is bisulfate ion. So this bisulfate ion dissociation constant is 1.2 10 to the power minus 2. So dissociation constant of sulfuric acid. In the first step, it is 10, and second step, it is 1.2 10 to the power minus 2. Sulfuric acid formed as it releases two H plus ions. It can form two types of salts. One is sulfates and bisulfates, like sodium bisulfate, NaHSO4, and second one is sodium sulfate, Na2SO4. So usually it can form with other metals. Two types of sulfates. One is bisulfate and another is sulfates and bisulfate. Calcium bisulfate, calcium sulfate. Like that it goes on. I hope it is clear. Next. Concentrated sulfuric acid acts as a strong dehydrating agent. As I already told you, it is a good dehydrating agent. It absorbs water due to its high affinity towards water. It chars carbohydrates to form black precipitate of carbon. So sucrose on reaction with sulfuric acid it forms carbon black precipitate along with water. So that's why it chars. Chars means it turns carbohydrates into black color precipitate due to the formation of carbon. Hot and concentrated sulfuric acid is a moderately strong oxidizing agent. So sulfuric acid is a strong oxidizing agent. It oxidizes copper to copper sulfate, sulfur to sulfur dioxide, carbon to carbon dioxide. So this concentrated sulfuric acid is a good oxidizing agent, strong oxidizing agent. It oxidizes copper to copper sulfate, sulfur to sulfur dioxide, carbon to carbon dioxide. So these are all oxidation processes. Addition of electronegative radical, addition of oxygen, addition of oxygen. I hope it is clear. So sulfate ion is SO4 2 minus. So if you take addition of electronegative radical also, it is coming under addition of electronegative radical, electronegative radical, because group of atom is joined together is called radical. So sulfate ion is nothing but it's a radical. So addition of electronegative element or electronegative radical is nothing but again oxidation. Nothing but what? Oxidation. So that's why here copper is oxidized by sulfuric acid to form copper sulfate. So copper changes to copper sulfate, sulfur changes to sulfur dioxide, carbon changes to carbon dioxide. I hope it is clear. Next, use of sulfuric acid. Sulfuric acid is very important industrial chemical. It is used in the manufacture of fertilizers, petroleum refining. It is used in the manufacture of pigments, paints, and dyestuff intermediates. It is also used in metallurgical extractions because many ores are sulfide ores only. And it is used in lead storage battery as battery electrolyte. This we have seen already in 38% concentrated sulfuric acid will use as electrolyte in lead storage battery. This is called secondary battery. This we have done already in electrochemistry. So 38% sulfuric acid, pure sulfuric acid, 38% sulfuric acid means it is nothing but 38% concentrated sulfuric acid and remaining it is dilute. So this is used in the lead storage battery and it is called a secondary battery, which is rechargeable. It is rechargeable. So this storage battery already we have seen in the previous chapter, that is electrochemistry, which we have already discussed. Next, it is used as laboratory reagent. So sulfuric acid, these are the common use of sulfuric acid. These are the common use of sulfuric acid. I hope it is clear. Next. Why concentrated sulfuric acid and calcium chloride or phosphorus pentoxide cannot be used as dehydrating agents for ammonia? Because ammonia is basic in nature and these are acids. Sulfuric acid is used as sulfuric acid is an acid, so it forms salt. That's why it cannot be used as a dehydrating agent for ammonia. Next. So now we'll discuss some more questions based on this sulfur. So some important questions based on sulfur. 16 group elements. Since we have not done many questions, in the next topic also we'll do questions based on 16 group elements. So please listen carefully. All the important models of 16 group elements. Basically, we'll get questions based on general properties. So that's why we'll do all general properties, questions based on general properties. So questions. MCQs. Question number 1. What is question number 1? The more chair form of SF sinks. So I'm writing here the answer questions. The oxidation numbers of sulfur. The oxidation number. This is previous IIT question. The oxidation numbers of sulfur in S8, comma H2F2 and H2S respectively are option 1, that is 0, comma plus 1 and minus 2. Option 2, that is plus 2, comma plus 1 and minus 2. Option 3, 0 plus 1 and plus 2. And option D is option B. So option D, it is minus 2 plus 1 and minus 2. Minus 2, comma plus 1 and the minus 2. So these are the 4 options we have. Let us see. So already we know the oxidation state of the elemental sulfur, that is S8 molecule, is always 0. So in this it is 0, and here it is S2F2. Fluorine is more electronegative than sulfur. So 2x minus 2, because oxidation state of fluorine is equal to minus 1 always. So 2x minus 2 is equal to 0. Implies 2x is equal to 2. Implies x is equal to 1. So that is plus 1. So this is plus 1. So 0 plus 1. Where we have 0 plus 1, we have this also. And finally, we know hydrogen is more electropositive than sulfur, so it will get minus 2. So answer is first option, 0 plus 1 and minus 2. 0 plus 1 and minus 2. Next. Next question. Which hydride is non-poisonous hydride? Which hydride is non-poisonous hydride? Which hydride is non-poisonous hydride? Option 1, water. Option 2, hydrogen sulfide. Option C, that is 3, selenium hydride. And option 4, tellurium hydride. So except water, all other hydrates are poisonous in nature. So answer is A. I hope it is clear. Second option is A. Next question. Question number 3. Third question we are discussing now. Which of the following is a weakest acid? Which of the following is a weakest acid? Which of the following is a weakest acid in its aqueous solution? In its aqueous solution. Option 1. Which of the following is the weakest acid in its aqueous solution? Option 1. Hydrogen tellurium. Option B, that is second option, selenium hydride. Option C, hydrogen sulfide. Option D, H2PO, that is hydrogen polonium. So answer is H2S because H2S is weakest acid in its aqueous solution. Down the group, as we go down the group, acidic character increases. Basic character increases, acidic character decreases, but acidic solution, which of the following is weakest acid, is hydrogen sulfide. Next question. Next question. The hybridization of sulfur and SF4 is the hybridization of sulfur in SF4 is sulfur tetrafluoride. Option A is given sp3d2, B is given sp3d, C is given sp3d3, and D is given sp3. So, how to find hybridization? Since already we know sulfur hexafluoride means sulfur has 6 electrons. So 1, 1, 2, 3. So it has 4 electrons. So total 6 electrons with 4 sulfurs. So it is nothing but what? 4 bond pairs, 1 lone pair. So 4 bond pairs and 1 lone pair. So n factor is equal to 5. If n factor is equal to 5, it is sp3d. N factor is equal to 6, sp3d2. N factor is equal to 4, sp3. N factor is equal to 7, sp3d3. So here n factor is equal to 5 because it contains 4 bond pairs and 1 lone pair. So n is equal to 4 bond pairs because 1, 2, 3, 4 bond pairs and we have 1 lone pair. So 4 plus 1, 5. So 5 is equal to sp3d. I hope it is clear. Next question, question number 6. In SCl2, that is sulfur chloride, SCl2, the central atom involves central atom involves first option sp3 hybridization, second option sp3d hybridization, third option sp3d hybridization, third option sp2d2 hybridization, and fourth option it is dsp2 hybridization, dsp2. So sulfur, it has 6 electrons in the valence shell and plus 2 monovalent atoms. So if you take the formula SCl2 also, even if you take that is 6 plus 2, so it is so if you take SCl2, simple again, ClCl, so it has 2 bond pairs and 2 lone pairs. So 2 bond pairs and 2 lone pairs. Total it is how much? 4. So since it is 4, so hybridization is n factor is equal to 4. So how much? What is the n factor? N is equal to 4. So it is sp3 hybridization. So central atom involves sp3. I hope it is clear. Next, question number 7. So these are all previous competitive questions. In SO2, in sulfur dioxide, two oxygen atoms are linked. Two oxygen atoms are linked to the sulfur atom, to the sulfur atom, the sulfur atom by double bonds. The two pi bonds are the two pi bonds, because they have two double bonds means definitely they have two pi bonds. The two pi bonds are, first option, both p pi bondings, that is p orbital of sulfur combined with p orbital of oxygen. Second option, both p pi d pi, both p pi d pi. And third option, that is p orbital of oxygen combined with d orbital of sulfur. Third option, both d pi, both d pi. And fourth option, we have one p pi and one p d pi. One p pi and one p d pi. So one p pi of sulfur and oxygen, one p pi of oxygen, one d pi of sulfur. So answer is fourth option, because in sulfur dioxide, some sulfur is having two double bonds with oxygen. So sulfur dioxide, so it has one p pi, and this is one p pi bonds, and this one becomes one p d pi bonds. Any one option. So answer is fourth option. Very, very important. So all these questions they are given for previous competitive exams. So that's why I'm giving now. Next question, question number 7, 8. Question number 8. In solid cyclic form of sulfur trioxide, each sulfur, this we have done in already sulfur trioxide allotropes. So each sulfur is surrounded by is surrounded by dash oxygen atoms. First option 4, second option 3, third option 5, and fourth option 6. So you know the cyclic form of sulfur trioxide is S3O9. So each sulfur is linked with 4 oxygen atoms. S3O9. The formula of sulfur cyclic polymer is S3O9. So please note it down. The cyclic form of sulfur trioxide formula is S3O9. This we have done in first slide itself. So it is each sulfur is surrounded by dash oxygen atoms, that is 4 oxygen atoms. Question number 9 now. Question number 9. In H2S2O2, H2S2O2, the oxygen state of sulfur is, the oxygen states of sulfur is, sulfur are option 1 +4, -2, option 2 +4, 0, option 3 +2, -2. As I told you, the oxygens are very important. and option 4D +4, -4. So for this, you should know the structure of H2S2O2. If you take the structure, S double bond S, OH, OH. So here this sulfur is having 1, 2, 3, 4. So this is +4, this sulfur is +4, and this sulfur only 2 is there, -2. So answer is +4 and -2 because this sulfur is attaching only with this sulfur only. So this sulfur is -2 and this sulfur is +4. So answer is +4 -2. I hope it is clear. So oxy acids of sulfur is very, very important as I told you. Next question, question number 10. The number of sigma bonds and pi bonds. The number of sigma bonds and pi bonds in sulfuric acid molecule is. So for this also we should know the structure of sulfuric acid. So sulfuric acid molecule. So option A 6 sigma 2 pi. Option B 6 sigma 0 pi. Option C 2 sigma and 4 pi. And option D 2 sigma and 2 pi. So first you should know the structure of sulfuric acid. Sulfuric acid structure is S double bond O, double bond O, OH, OH. The structure of sulfuric acid. So 1 sigma, 2 sigma, 3 sigma, 4 sigma. And here, so this is structure. And here OH also is suddenly again linked with one more hydrogen. So OH also linked like this. So we have totals. For double bond, we have 1 sigma bond, 1 pi bond. So 1 sigma bond, 1 pi bond, 1 sigma bond, 1 pi bond, 1 sigma bond here, 1 sigma bond here. And for this OH also 1 sigma bond, 1 sigma bond. So total it is 1, 2, 3, 4, 5, 6 sigma bonds and 2 pi bonds. So answer is 6 sigma, 2 pi. I hope it is clear. Again, if you want, I write here S double bond O, O, H. This is also O, H. This is again double bond O. So 1 sigma, 1 sigma, 1 sigma, 1 sigma, 1 sigma, and here also 1 sigma. So total how many? 1, 2, 3, 4, 5, 6 sigmas. And double bond is means 1 pi bond, 1 pi bond. So 2 pi bonds. So 6 sigma, 2 pi is answer. I hope it is clear. Next. So with this, I'm completing this class. The next session we'll do more about. In the next session, we'll do more questions based on this. So explanation part of this chapter is finished. So next session, we'll do more questions based on 15th group and 16th group. I hope it is clear. So please do more questions on 16th group elements. It will be very easy for you to understand. I hope it is clear. Thank you.